Hello guys, in the previous video we have talked about linear expansion of solids. In this video we are going to talk about areal expansion of solids. So we can create some relationship between areal and linear expansions, or you can create some analogy between areal and linear expansion, because it is all about approximation the amount of change in area. In this case, in the previous case, we have seen how to approximate the change in length on a certain thin long wire, maybe due to the change in temperature. So last time we have said that the change in length due to heating increases with the length at the colder temperature, and it is also increasing with the change in temperature itself. So the change in length is proportional to the length at the colder temperature times the change in temperature. The concept of proportionality is very important to investigate your science. So this proportionality is turned to equality by introducing a constant. So the change in length is equal to the constant times the length at the colder temperature times the change in temperature. And this change in length is equal to alpha, which is the coefficient of linear expansion, times the length at the colder temperature times the change in temperature. And we have noted that the change in temperature is the temperature hotter minus the temperature colder. And we have another equation for the change in length. It is the length at the hotter minus the length at the colder. And instead of this one, you can put the expression we derived here. So the length at the colder times alpha times change in temperature is equal to the length at the hotter minus the length at the colder. So you can have expression for the length at the hotter. You can write the length of a wire as a function of temperature. So when you move this one here, you're gonna get the length at the colder times alpha times delta T, change in temperature. Change in temperature equal to, plus this LC, this one is equal to the length at the hotter. So when you take the common LC, so the length at some hotter temperature is equal to the length at the colder temperature of the same wire times the coefficient of linear expansion times the change in temperature plus 1. Or you can write length of the wire at some T hotter temperature is equal to the length at the colder temperature into 1 plus alpha times the length, the temperature, this is the hotter temperature, minus the colder temperature. So this is the expression we have derived last time for the change in length. Now let's have expression for the change in area. Analogous to that of the change in length, we can have the expression for the change in area. Consider this rectangular thing, then it is the red one represents the length, the area of the plane at a colder temperature, and when you heat it, every dimension increases. So the thing we did here is this factor is approximated to be 0. The change in area is very small, and the change in length is very small. The square of the change in length is also very small, so it can be ignored. Now, how do we have relationship? How do we take the analogy? So the analogy here is the change in area dependent on the area at the colder temperature, and it is also proportional to the change in area is also proportional to the change in temperature, like the linear case. So we can have a comparison here. Linear is here. We can have a linear coefficient of expansion. So linear, and you can have areal here. You can compare. So we have said the change in length is equal to the length at the colder times temperature coefficient times the change in temperature. But there is a certain analogy here. The change in area is equal to the area at the colder temperature times beta which is the coefficient of volume, areal expansion. Usually for solids, beta is 2 times alpha times the change in temperature. So the only difference is to get the beta, you double the coefficient of linear expansion. So there is no specific areal expansion or volume expansion for solids. So for solid, you triple the linear expansion. For volume, when you find the volume coefficient, you triple. For areal coefficient, you double it. So the other expression is, then you have this relation, and the area of the solid at some temperature T is given by, like the previous one. We can derive this from the bottom like this. So we have two equations for areal expansion, change in area. So change in area is area colder, beta, times change in temperature. This is the same as area hotter minus area colder. So let's write expression for area hotter. So you can ignore this. So take this equality. So area hotter minus area the colder area minus area colder is equal to area colder times beta times change in temperature. So move this one to here. So we're gonna get we are going to get the next expression, that is the area, the change in area, this area hotter is equal to area colder plus area colder times beta times the change in temperature. Now what gonna be the expression for the area final? So we have the change in the area hotter. We have the area hotter temperature is equal to the area at the colder plus area at the colder times beta times change in temperature. But you can write this one as 1 times area colder plus you can write this one area colder times beta times change in temperature. So these two terms have area colder common. So the area at the hotter is equal to the area colder into 1 plus beta times the change in temperature. But the change in temperature is T hot minus the colder. Now I can write the area of a certain plate as a function of temperature. The area of a plate as a function of temperature is equal to the area at some colder temperature times 1 plus beta into the temperature hotter minus the temperature colder. That's it. This is the expression for the volume, the area as a function of temperature. Thank you for watching. Let us do this example. An iron plate, alpha for iron is 1.1 times 10 to the power of minus 5 k to the power of minus 1. So we are given the following things. We are given the area colder is given. The area at the colder temperature is 2 times 10 to the power of 6 millimeter square, 2 million millimeter square. And the temperature colder is given, it is 30 degrees Celsius, and the temperature hotter is given, it is 80 degrees Celsius. And we are also given the coefficient of linear expansion. It is 1.1 times 10 to the power of minus 5 k to the power of minus 1 is given. Now from this your beta is double of this alpha, 2 times alpha. This is equal to 2 times 1.1 times 10 to the power of minus 5. So this is equal to 2.2 times 10 to the power of minus 5 is our coefficient of areal expansion. This is our beta. And the change in temperature, from this the change in temperature is temperature hotter minus temperature colder. So that is 80 degrees Celsius minus 30 degrees Celsius gonna give us 50 degrees Celsius. So this is 50 degrees Celsius. We have everything. Now let's have the equation. So let's do the change in area. The change in area is equal to the area at the colder times beta times the change in temperature. So the area is 2 times 10 to the power of 6 millimeter square times the coefficient is 2.2 times 10 to the power of minus 5 k to the power of minus 1, and the change in temperature is 50 times 10 to the power of minus k to the power of minus 1, k to the power of not 10, it is k to the power of 50 k to the power of 50 per Kelvin. Now let's calculate this. Okay, all right, now we have 2 times 2.2 times 50 times 10 to the power of, we have 6 here times 10 to the power of minus 5 there. So it's better to do like this. So 2 times 2.2 is how much? It is 4.4 times 50, all right, is equal to, I mean this times 15 times 10 to the power of 6 plus negative 5, or the unit is millimeter square. Now 44 times 5, how much is 44 times 5? 5 times 4 is 20. You got 2 4. This is 5 times 4 is 20 again, 22. So this is 220 times 10 to the power of 1 millimeter square. So this is the same as this is 220 times 10. So this is 2200 millimeter square. That is the change in area. The change in area is how much? The change in area is when you heat iron from 30 to 80 degrees Celsius. If the initial area was 2 million millimeter square, so the area at the 80 degrees Celsius gonna be 2200 millimeter square. Now what else? The area at the final temperature is required. The area at the hotter temperature is the area at the colder temperature plus the change in area. So the change in area is already done there. So 2 million, this is 2 million plus 2200, I'm sorry, 2 million, all right, sorry, so this is no, 2 million times, yeah, 2 million millimeter square, okay, plus 2200, no, 2200, 2000 200 millimeter square. So when you add this, you get area at the hotter is equal to 2002, all right, then 200 millimeter square, 2,200 millimeter square gonna be the final area. Now let's compare linear expansion of solids. We get the change in length, which is equal to the length at the colder temperature times coefficient of linear expansion times the change in temperature. For areal case, we have change in area is equal to the area at the colder temperature times coefficient of areal expansion times the change in temperature. The same thing is true here, but we modify this. The change in volume is equal to the volume at the colder temperature times gamma, coefficient of volume expansion, which is gamma is 3 times coefficient of linear expansion, but here beta is 2 times coefficient of linear expansion, so times the change in temperature. Now the certain analogy here we are going to take is The change in volume due to heating a certain solid is proportional to the volume at the colder temperature, and the change in volume again is proportional to the change in temperature. So from this we have the change in volume is proportional to the volume at the colder times the change in temperature, meaning the change in volume due to heating is the volume at the colder times the change in temperature times a constant. That constant is called the coefficient of volume expansion, that is gamma. So the change in volume is how much? Gamma, 3 gamma, not a single gamma because it's 3-dimensional. You can simply reason out 3 times coefficient of linear expansion times the volume at the colder times the change in temperature. So this is the expression for the change in volume due to heating, but this is related to the other factors. So the change in volume has two equations. One is V colder. Sometimes some literature say V naught or VO. So the colder volume times the change in temperature times 3 times alpha. But this is the same as the volume at the hotter minus the volume at the colder. Now let's equate these two. When you equate these two, we are going to have the volume hot minus the volume colder is equal to the volume colder, this one, times what? Change in temperature times 3 times the coefficient of linear expansion. Now transfer this one to there or here. So the volume V at the hotter is equal to the volume at the colder plus the volume at the colder plus change in temperature times 3 times alpha. But you can say this is the same as the volume at the hotter is equal to 1 times the volume at the colder plus volume at the colder times 3 times alpha times the change in temperature. But these two terms, this guy and this guy, have something common. The VC is common. So the volume at the hotter temperature is the volume at the colder temperature into 1 plus 3 times alpha times the change in temperature. Now it's time to write the volume at the hotter temperature as a function of the temperature. So the volume at a certain hotter temperature T hotter is equal to the volume at the colder temperature V of T colder into 1 plus 3 times the coefficient of linear expansion of the material times the temperature hotter minus the temperature colder. This is a function that relates the change in the volume of some object at a certain temperature. Now let's have this example. A cylindrical container made from iron, coefficient of linear expansion is 1.1 times 10 to the power of minus 5, has a volume of 360,000 millimeters square at 10 degrees Celsius. What will be the change in volume? We're looking for the change in volume and its volume at 60 degrees Celsius. This time we are given the volume, the colder is given 3.6 times 10 to the power of, you can shift 1, 2, 3, 4, 5, 10 to the power of 5 millimeter cube, yeah. And what we have is the temperature hotter is 60 degrees Celsius. 60 degrees Celsius. The temperature colder is 10 degrees Celsius. So from this we have the change in temperature is 60 minus 10. This is 50 degrees Celsius. So alpha, we need the volume coefficient. Okay, now we require two things. The change in volume is how much? The volume at the hotter is how much? Let's do this. Alright, the formula for the change in volume is volume at the colder times 3 times alpha, which is gamma. This is gamma times the change in temperature. So this is 3.6 times 10 to the power of 5 millimeter cube times 3 times alpha is 3.3 times 10 to the power of minus 5 k to the power of minus 1, and the change in temperature is 50 k to the power of minus 1. So So this is equal to the product 3.6, sorry, 3.6 times 3.3 times 15 is 594 times 10 to the power of minus 5 plus 5 plus minus 5, that is 5 10 to the power of 5 plus minus 5. So this is 594 millimeter cube. So that is the change in volume. The change in volume is equal to 594 millimeter cube, and the volume at the hotter is equal to the change in volume plus the volume at the colder. So this is equal to 594 millimeter cube plus 3.6 or 3.6 times 10 to the power of 5 millimeter cube. So this is equal to 360,594 millimeter cube. This is the volume at a hotter temperature, meaning the volume at 60 degrees Celsius. Thank you for watching this video.